Okay, תודה. I'm Oren Etzioni, and for those of us who are working in big data, we're always alert to trends, right? So we started with the president of the Technion, then we had the dean, then we had the founder of TCE. So clearly we're on our way down in terms of stature. So, but hopefully I can share with you an entertaining talk about the future of search. I like to start with the notion of information overload and the fact that we're exposed to just a ridiculous amount of information every day. And that's a problem that's just getting worse. And you might say, well, that's okay because we have technologies that can help us. We have Google. Well, as they say in Seattle, Google can't satisfy every search. And Mitch Kapoor has a great line. He says, getting information off the internet is like taking a drink from a fire hydrant. The other thing that's going on is we have the explosive growth of mobile devices, right? Google recently announced that the number of queries from mobile devices has exceeded the number of queries from desktop machines. So that effectively means that we're trying to drink information from a fire hydrant, but we're trying to use a straw. Right, a very small device. So that's the problem that motivates a lot of my research. And in a paper in Nature a couple of years ago, I said, why don't we think about search over a much more semantic space? So instead of keywords and documents, think of entities and predicates. Instead of algorithms like TF-IDF and PageRank, think of the graph of relationships, and I'll get into more detail in a bit. And then instead of the dread 10 blue links, a list of documents to go to that you don't have to read on a tiny mobile screen, instead think of question answering. What restaurant should I go to tonight that has space available, et cetera, et cetera. And shortly afterwards, Google released their knowledge graph, which I assume people are familiar with. Facebook released their graph search. How many people have used Facebook graph search? Okay, only a small number. And I wish I could say that these projects were inspired by my article, but that's clearly not the case, right? It takes a long time to gestate these things in big companies. But I think we're all pointing in the same direction of trying to have interactions that are much more question-answer based rather than traditional information retrieval search. And in the case of Facebook graph search, the idea is that you can ask questions of the forum, show me all the photos by friends of mine who grew up in Tel Aviv, or show me all the pages that people I went to high school with liked. So it's a very nice setup. The only problem is it only operates over structured information in the Facebook database, over photos, over friend relationships in the Facebook graph, over likes. It doesn't look at all at the posts that people have done, what texts they've created. Let me show you what the Google Knowledge Graph looks like. Here, if I query about Michelle Obama, I see on the left the traditional layout of results, and I see on the right Michelle Obama, some pictures of her, and about maybe 6 or 7 key facts about her. Of course, they turn out not to be, I think, the facts that most people are interested in, right? They're talking about, her siblings. We know who her spouse is. The big question about Michelle Obama is, how did she get those arms, right? So anyway, and I think what this shows is that the Google Knowledge Graph really is a split personality. And the reason I say that is on the left you have information generated from text. It has very high recall. Pretty much any query will get you some documents, but you have to read them, and often they're the wrong documents. Here on the right, you have a very limited amount of information. Thus far, it's been garnered from databases, right? And it's meant to be almost 100% correct, right? And so if it's going to be 100% correct and coming from databases, clearly the recall or the scope is going to be very limited, right? And so they say, let's put them both on the page and see how people react. And the direction I want to point to, I want to say, well, can we take all of this stuff, everything that's in the text, and put that in a database as well, a database of some sort, right? That's a much more ambitious undertaking. And as far as I know, Google is actually trying to do that, but obviously it's a very hard problem. So now the outline of my talk, I'm going to talk about a set of techniques called information extraction, or IE for short. We apply them to text to get some notion of knowledge, to get some structured information. I'm going to not define these terms very formally. The key thing here in the context of big data, I'm really talking about big text. Okay, so this isn't so much algorithm operate over numerical data. These are algorithms that operate over large corpora of text, and particularly the text on the web. So what am I going to say? I'm going to talk about exactly what is IE and how do you do it. I'll explain that at a very high level. I'll show you some fun examples of IE in action over reviews, over news and tweets. And then I'll talk about OpenIE, which is attempting to apply IE at web scale. I'll show you a demo and a video if it all works, and I'll conclude with a discussion of future work. The key technical ideas are twofold. Number one, IE, as so many things these days, turns out to be an instance of machine learning or data mining. I'll show you that. And two, the key question is, how do we scale it? How do we scale IE to the entire web? Okay, so a little bit more specifically, IE is a function that maps sentences to structured tuples and associated probabilities. So for example, if I have, by all accounts, Edison is credited as the inventor of the light bulb, I should be able to map that to the predicate invented, applies to Edison and the light bulb, and I know this fact with very high probability. That's the sort of thing that we're doing. And the question is, how do you do that, right? It's actually a pretty magical thing, right, to go from arbitrary sentences to something a lot more structured like this, and to do it with high confidence. And so the basic idea is that we use the context of words as clues to their meaning. And this is an idea that goes back to the 50s of the previous century. First said, you shall know a word by the company it keeps. It sounds almost biblical. So here's the idea in a very simple way. Let's say I see the string Nurja. Anybody know what Nurja is? Yeah, me neither. But now I see a sentence that says Nurja Mayor. Another sentence talks about downtown Nurja. Another sentence says Spanish towns such as Barcelona, Nurja, etc. I now start to have a much clearer notion of what Nurja is based on the context, right? So now, of course, you have to be careful with this notion of context. Here's a sentence, countries such as Garth Brooks, right? Garth Brooks is not a country, right? And this is really a case of what's called ellipsis. It's meant to be country music, such as Garth Brooks's, etc. So we do need to be a little bit careful when we use the context. We probably want to use multiple pieces of context and associate probabilities with our conclusions. But a big question is, where do these clues come from, right? You're familiar with words like mayor and downtown and such as, but how does the computer get the idea of what are these clues and what do they mean? And the answer is that we can actually learn these clues from labeled text. So let's say the relation I'm interested in, or the target concept, is cities. And so I could take sentences that are hand-labeled and use them as training examples. So I would say, okay, the sentence with the mayor of Madrid, I'm going to label this sentence as an example where Madrid is a city in the sentence, and likewise with downtown Madrid, and so on and so on. And now I can learn that the words in red here are context that allow me to discover unknown cities. That's the basic idea. And so most information extraction systems have a very simple loop with 3 steps. We take some sentences and we label them with examples of some relation R. We then extract automatically the frequent context of R as these clues, and then we use these clues to find more examples. That's the basic loop of probably 99, 98% of information extraction systems. And there's a lot of fancy enhancements. Okay, you can do mutual recursions, right? As you find more examples using the clues, you can then find more clues. Using more clues, you can find more examples. We could try to figure out how to get negative examples. The NEL project at CMU does that. We could use a parser over the sentence to get more information about the sentences. But all these are enhancements of this basic loop. And it turns out this basic loop is very effective, but there's some problems in scaling this, particularly the fact that step one is a manual step. Okay, this labeling process is a hand labeling process. Now, with that said, let me show you some examples of information extraction in action. So, excuse me, let's look at the case of product reviews. It turns out that product reviews are very helpful for people who are shopping, but it's actually hard to aggregate the information across a bunch of reviews. You have to read a whole bunch of them to make a clear decision about which restaurant to go to in Tel Aviv or which hotel to stay in New York. Turns out there's a lot of phony reviews. There's all kinds of outliers, right? People who say crazy things. It's also difficult to focus on the key attributes, okay? So you have all these hotels, and people are saying good things about them, but they're talking about the concierge, they're talking about the location. I'm a light sleeper. What I really care about is the hotel quiet? So I really have to comb through the reviews in detail to find out where I can find a quiet hotel. It's also impossible to sort on the attributes. I can sort on the star ratings, but again, what I want to do is sort on the hotel that is the quietest. And I can't do that using reviews today. And then lastly, it's difficult to actually read the reviews and do all this on the phone. And yet, a recent study showed that people who are in stores, 24% of the time actually use their phone to look up the reviews and to try to read through them. So, in a research project at UW, what we did is we took about 300,000 Yelp reviews about restaurants in Seattle, and we extracted the key attributes from them. And you see why we need to do this. For example, here's a search for good margaritas in Seattle. And if you look at the information, I don't know how well you can see this, but this doesn't at all talk about margaritas. Here it says good intentions, and here it says good coffee. It's not really talking about good margaritas. Moreover, if somebody said tasty margaritas or exquisite margaritas, it wouldn't match the search, right? But in fact, that's highly relevant information. So Jeff Wang and I, back in 2012, we took these restaurants at input, we ran an extractor, and it identified automatically the key attributes like the dim sum or the server or whatever it is people were frequently saying about restaurants. It associated with each of those a value that's an opinion word, like the dim sum is delicious, the server was rude, and then it clustered these attributes into certain categories like food and service. And then you could issue a query like good margaritas and get the results sorted by sentiment from strongest positive sentiment to weakest. And this is what it looks like on the phone. You see extracted attributes like pizza or the crust. This is for a particular pizza place called Serious Pie. You'll see they talk about the place, the table, et cetera, et cetera. And this is available on the web at revminer.com if you just want to play with it and see what the state of the art is in extracting attributes and values from restaurants. And again, this is a work of a student over a few months. So this technology is quite practical. Some of you may be aware Yelp just released a data set with a whole bunch of restaurant reviews in Phoenix. They have a competition, so we've entered the competition with our extractor. We'll see how well we do. Let me show you another example of what we can do with text, and this is at the company I founded, Decide.com. our idea is to eliminate buyer's remorse. And we do that in a number of ways. But one of the most annoying things is when you buy, I don't know, an iPad 3, maybe 3 weeks before the iPad 4 comes out. And now you're stuck with a 3, and the 4 just came out, and of course the 4 is much better, right? So we don't want that. And so one of the things we do automatically is the science technology crawls literally thousands of news and rumor sites about consumer electronics, blogs, PR announcements, whatever it can find, from MacRumors.com to Android Police. And what it does is it looks at the text and tries to extract information of the forum. Is there a new model coming out? How reliable is it? When is it coming out? Et cetera, et cetera. So it can warn you, hey, don't buy something that's about to be antiquated. And let me show you some current examples. So this is, if I click through here to decide.com, this is a particular Toshiba laptop. And assuming the internet Wi-Fi cooperates with me, maybe stop reading your email for a second. Okay, so this is what it looks like. We find out that the site tells us the Toshiba satellite is highly rated, and this is based on a bunch of reviews. We can delve into that in a second. But there's a new model rumored. And if I'm curious, well, what does it mean, new model rumored? I click on this, and I see that it's rumored that the next model is coming out very soon, June 2013. Here are the new features that it's going to have, including touchscreen options, updated graphics options, and so you may well want to wait for that. And again, if you want to read more about it, here below here we show you where this rumor came from. This is from PR Newswire, a very recent press announcement that you might have missed. Right? So the idea is there's so much text out there that really you don't want to read, and it's not Shakespeare, right? Looking at an announcement like this and getting out, okay, a new model is announced, this is the date, is something that very much we can do. The other thing I wanted to show you is what it looks like when we analyze the reviews. So for example, we boiled down the reviews into a few categories. And for example, if we look at battery life, and by the way, this technology is not always perfect, so let's have a look. We'll see that there are 4 positive things that were said about the battery life. And I don't know if you can see, but somebody says, battery life is great. Great battery life, the battery life is good. So that's nice. And likewise, but there are 3 negative reviews. Somebody said poor battery life is kind of short, et cetera, et cetera. About the display quality, there are 34 positive reviews, 0 negatives. So the great thing about this is once you get comfortable and you feel like you can trust our extraction technology and you can play with it, and it's not perfect, but it's quite good, you can see a very concise summary, right? These green bars and red bars are something that's much more palatable, particularly on your phone, right? And we have an iPhone app, and so you don't have to read reams and reams of text to get a sense of what are people saying about this device. Okay, so this is what we can do today. I have another example with vacuum cleaners, but in the interest of time, video games, interest of time, let me move on. So you've seen very quickly, i.e. in practice, pulling key tidbits out of text. There's some problems with conventional IE. Basically, each relationship that you extract, each predicate, you have to train a special classifier or a special extractor, and that's based on hand-labeled training examples. And so that's a real problem, and it's really difficult to scale. So if we're talking about big text, and specifically all the text on the web, then we have a real problem. So I wanted to show you a quick video at this point describing our project, also introducing some of my colleagues and students that worked on this project so they get a little bit of recognition as well. Open information extraction is the ability to glean facts and opinions from a huge number of sentences, literally billions and billions of web pages.
What we want to be able to do is take the information that's already out there, that's already on the web, already in different web pages, and then just curate it, put it together into a usable form.
The future of the project is to then tie in knowledge representation, inference, and machine learning. So we start with the information that's extracted, we learn from it, we form generalizations, and we infer things that weren't even said in the original text.
The key difference of what we do compared to Google Knowledge Graph is that we can get facts about anything, and we don't have to tell the computer to do it ahead of time.
Google goes one step short of open information extraction because they actually have to choose what they're targeting. So they only target certain pieces of information. Open information extraction, the open part, means we target any relation, so we can go after any fact.
Let me give you an example. What cities are business capitals? So here you can see that we get Mumbai as the business capital of India, Sydney is the business capital of Australia, Toronto, Canada, New York City, the world, and so on.
For another example, with OpenIE, we can search for kills bacteria and quickly get a list of many different types of things that kill bacteria, such as antibiotics or chlorine. We can also further divide these answers by their types. For example, we might be interested in just the drug ingredients that kill bacteria, tea tree oil and hydrogen peroxide.
The goal of OpenIE is not just to extract facts from text, but also to understand them. One of the ways in which OpenIE understands these facts is by mapping argument strings to world entities, say in Freebase. For example, when asked which drugs are approved by FDA, OpenIE gives us a long list. However, in this list, many of these entities like Celebrex are not the entities that it was able to map to Freebase. However, it still knows that these are drugs, and that is because of its type inference algorithm.
Our goal is to build the next generation of search engines. No more 10 blue links that you have to go through, read, click on, etc. Instead, you ask questions, you get answers. To demonstrate the utility of OpenIE, we applied it to hundreds of thousands of restaurant reviews in Seattle in a project called RevMiner. So for example, you could ask about good sushi in Seattle. You'll get the list of restaurants ordered by who's got the best sushi. Exquisite sushi is ordered ahead of good sushi, and good sushi is below great sushi. So there's sentiment analysis, and we automatically capture the strength of the sentiment. We sort by that, normalize for the number of reviews, and give you what we think is the best sushi place in Seattle.
We have put a huge amount of effort in releasing the code for OpenIE. If you have your data, be it from any domain, news, politics, sports, biology, what have you, you can download our software and run it on your data, and you would be able to interact with your data and ask pointed questions in completely novel ways.
We've been working on OpenIE for almost a decade, but there's still a lot of work to do. We need to improve the precision and recall of the techniques. We need to go deeper into the text and understand better what people are saying. We need to tie what's extracted to background knowledge, to inference, and we need the ability to form generalizations based on it. So some of the hardest and most interesting AI problems are just coming to the fore right now. Join us at the University of Washington in Seattle. So excuse me for the commercial, but we are looking for students, postdocs, and so on. So you know, please come see me if you're interested in joining us. So again, what's the basic idea here? And I like to use the phrase "no sentence left behind," and we're only focused on English right now, although recently I learned somebody came up with OpenIE for Spanish. I think it would be easy to build an OpenIE system for Hebrew. And the idea here is the following. Relations are not pre-specified, right? Think about it. When you pick up the newspaper in the morning and you start reading it, does somebody tell you, okay, I want you to focus on this particular predicate? No, it's much more serendipitous, open-ended process. The same for OpenIE. The relations are not pre-specified. We don't have hand-labeled examples, and we make a single pass over a massive corpus. Since we've introduced the idea in 2007, there have been about over 1,000 technical articles on this, according to Google Scholar. So our first system that did this was in 2007. It was called TextRunner. It extracted on the order of 1 billion distinct extractions. At peak precision was 0.9, although that was definitely at limited recall. We've also released open source extractors, and I met some of the students from Ido Dagan's group at Bar Ilan. They've downloaded it and are using them, and these are freely available for research. What are some of the highlights today? One is we're up to 10 billion extractions. We're about to release a corpus on ClueWeb 12, which is the latest research corpus. Again, as I said, there's no predetermined vocabulary. And let me show you some of these other points more in context of our demo. So I'm just going to go through a couple of examples, kind of like in the video, but a little bit more slowly. So one of the things we can do is we can just have simple natural language questions. When you click on one of these, which are our favorite examples, it maps it into one of 3 triples, right? So argument 1 is blank. We're looking for values for argument 1. Argument 2 is the relation, that's kills. And the third argument is bacteria. Now we say search. And when it comes back from the cache, it's even faster. And here we see the variety of things that it believes kills bacteria. And you see these are gathered from a very large number of web pages. So the number here, 442, is the number of places in the corpus that we saw that answer. The places where an answer is in bold is a place where we were able to link the answer to a particular value inside of Freebase. And so we have a bunch of background information here. We have associated types. And also, if you want to see, these are the sentences that this came from. And you see that the answers are, pretty good. And after a while, they start to be more kind of interesting and speculative, like vinegar, and so on and so on. We really do kind of a popularity contest. Tea tree oil, I didn't know that, et cetera, et cetera. I would say we probably have the best answer to what kills bacteria anywhere on the web. Another thing we can do, we can also use types. So if I want to ask what foods are grown in which countries, I say argument 1 is of type food, the relation is grown in. Argument 2 is of type country. I hit search. And it analyzes the different things. It's able to compute their types. Again, we wrote papers on this. And you see things like saffron is grown in Spain, cocoa beans in Ghana. This is kind of a fun one. No coffee is grown in Italy. And when I click on this, I see that, in fact, this is a relatively little-known fact. There's great Italian coffee that's roasted there, but it's not actually grown in Italy. So, this is far from ready for prime time. I don't use this as my search engine. I use Google. But you can start to see how these kinds of pointed questions and these very small answers might fit nicely on a phone screen. And over time, our goal is to very much get to the point where you can ask simple questions and get very concise answers based on information that's gathered from a very large number of web pages. I want to keep going, so I'll leave time for questions. The key to this technology is the incredible richness of the relations that we extract. So from tumor growth, if you think about biology, to joining forces, winning an Oscar, patron saints, writing the book, this is completely domain-independent stuff. And that's the key to this. To give you a sense of that, I compare here the number of relations we have in our systems with previous ones where the relations are developed manually. And you see that, Yago is on the order of 100, and L is 500. VerbNet, we go up to 5,000. But we have on the order of 100,000 and even millions of relations. Now, in fairness, these are not fully normalized, right? That's one of the tricky things. We're actually working on that. But it just shows you the richness of predicates that are missed by these systems. And the same, of course, is true of Freebase, and you saw a hint of that with Michelle Obama, right? There's so many things we could say about Michelle Obama, and it shows a very small number of predicates. We've done work doing this on Twitter. This is the work of Alan Ritter. We applied a kind of information extraction to Twitter, again, dealing with the arbitrary nature of stuff, and we were able to find interesting events, associate them with different dates. This is a snapshot from January, so we can do this with really pretty much any text. And where are we going with the project now? The next step is to allow much more sophisticated questions. And so this is a paper by my student Tony Fader that's about to appear at ACL. And his work goes all the way from asking an arbitrary question in natural language to answering it based on arbitrary text. So not just structured queries or very simple things like what kills bacteria, but you can ask pretty much anything and it'll try to come up with the answer. We're still working on improving the precision and recall of that, but if you compare that, those of you who might be familiar with the work on natural language interfaces to databases, this is far, far richer. Again, the set of predicates we have is 4 orders of magnitude bigger than your typical NLIDB system. The next step also is to tie this with inference. It turns out no matter how many sentences you process, it's still the case that a lot of the information that you want is still implicit. You'll see that it says that the University of Washington is in Seattle, but I need to infer that the University of Washington is in North America. Nowhere does it say that explicitly. It does a very simple inference, but we need our systems to do that. Another thing we're very excited about is linking our extractions to the linked open data movement, right? Just the massive amounts of manually and automatically generated structured information. How do we tie that to text? And we're also interested in dialogue above these systems. So really, there's kind of a triangle here. What we want to achieve is comprehensive knowledge with very high quality. And what we have today with the OpenAE demo, which you can play with, is some knowledge. Turns out it's not nearly as comprehensive as we'd like, and also it's not nearly as correct as we'd like. Okay, so it's a university research project. It's not Google. And the building blocks that we have are we want to have open-ended learning. We don't want to restrict ourselves to a specific narrow vocabulary. And we want to do tractable reasoning over this open vocabulary. And here, what there should be in the middle of this triangle is a big question mark. How do we do that, right? How do we tie these pieces together to achieve a comprehensive knowledge base? That's the goal of our project, and I hope I've enticed your interest to join me. Let me just summarize and then open it up for questions. So our long-term goal is, again, very ambitious. Imagine a machine that reads text automatically, reads all text, and tries to convert that into knowledge. It has infinite patience, right, to read all the text that we're overwhelmed by and giving us only the subset that we need. That's the dream. How far have we gotten? Well, I think we've shown you that we've gone from keyword search to extractions and relations, and also practical applications of that today in Decide.com, RevMiner.com. Other companies are using extraction as well. Google just acquired a company called Wavy that used the form of open information extraction. Hopefully I showed you very briefly how IE is just a form of machine learning, and the big question is, where does the labeled data come from? And I should emphasize, this problem of hand-labeled data isn't just, well, I need to have a lot of people label the data by hand, because you can always say, well, why don't I just use Mechanical Turk or some folks in the Philippines and pay them a small amount of money to label enormous amounts of data. The problem with labeled data is, well, labeled data for which concepts? And if I want to be serendipitous, if I want to allow arbitrary concepts, I don't know a priori what to label and how. That's the challenge here. And then what OpenAE does, it actually uses the structure of language to achieve scale. It says, I'm going to look at a sentence, And instead of using the hand-labeled data, I'm going to look at the structure of the sentence and say, okay, I think I know what the relationship is here. Let me extract that automatically, as I said again, without the hand-labeled data. And then where we're going is towards open question answering and reasoning on top of that. Thank you very much.